4.3 binomial distributions. So a binomial probability distribution is a distribution with these characteristics here. Okay, so first there's a fixed number of trials, and we obviously call that n. Okay, so it's fixed. It'll tell you like the die was rolled 6 times, for example. Okay, and there's always 2 outcomes. There's going to be a success and a failure. Okay, a success, I might give you the probability of a success, and then a failure is just 1 minus p, so the probability of success, and that's going to be your failure. Because we know that p plus q is going to equal 1 because there are only 2 outcomes, right? Binomial, 2 outcomes. Then this probability of a success plus the probability of failure is going to be all of the probabilities, and all of the probabilities added up will be 1. Okay, and these trials are all independent. So like as you continue to repeat all the trials, the probability does not change. Okay, in other words, replacement is a thing here. So here is the formula for the probability in a binomial distribution. So p at x, obviously that's the probability of x. X is just going to be your random variable, like what you want the outcome to be. Okay, what we're actually talking about in the question. Okay, so there's 3 parts to this. We first start with a choose function. N choose x. So n is the number of trials, and we're going to choose the number of successes, okay, that we want. And then we're going to do probability of a success times the number of successes, right? P to the x. And probability of failure, which is q, times the number of failures. And if you think about x and then n minus x, they equal n. Okay, so we've accounted for every single trial n. Okay, and the expected value for binomial distribution, the short form for it is n times p. So we don't actually have to do a full probability distribution chart and then add up all the probabilities or the XPXs for the expected value, I should say. We instead have this short form, n times p, which is just the number of trials times the probability of a success. So let's take a look at example 1. Okay, and I'm going to leave this here up top to reference. Okay, so example 1, 3% of batteries last for less than 10 hours. So while we're reading this, we have to think, is a success lasting less than 10 hours, or is a success lasting 10 hours or more? Okay, and don't think of it as like, ooh, success, it's lasting for longer. No, like read the question and see what the question's asking. So a success in this case may be that light bulb failing, for example. Okay, so now what is the probability that 3 of your 5 batteries last for less than 10 hours? So this is our focus. Our focus is last for less than 10 hours. That makes our probability of a success 3%. And then if we do Q, which is 1 minus P, we're going to get 0.97. These two here are going to add to 100%. They can be decimals or they can be fractions. And our N is 5. We're repeating this 5 times. So we have 5 batteries. So the probability that 3 of the batteries will last less than 10 hours is going to be, okay, we have 5 batteries, we're choosing 3. The probability of a success is 0.03, and we're going to have 3 successes. Probability of a failure is 0.97, and we're going to have 2 failures. So a couple highlights here. These 2 exponents are going to add to all of your trials. So 3 plus 2 is going to add to this. Okay? These 2 here, the 3 and the 3, those are going to match because they're the number of successes. Okay, and if we actually calculate this, put 5 choose 3 times 0.03 to the exponent 3 times 0.97 to the exponent 2. And we get 0.000254 and so on. Okay, so very, very little probability that 3 of the 5 will last for less than 10 hours. Okay, which makes sense because it's only 3% of the batteries. So therefore, if we move this over, it's 0.02, let's round 3%, that 3 batteries last less than 10 hours. Okay, we're going to take a look at more probability, like the rule of thumb, the indirect method. Okay, so more probability applied to these questions now. Okay, so a candy store bags candies, 30% which are red. Vanessa has 10 candies in her plastic baggie. Okay, so 30% are red. We're dealing with 10 candies. So when we talk about, say, A, what is the probability that 6 of Vanessa's candies are red? So 6. Okay, that's going to be our X. But our probability of success, now that we're focusing on red, we know a success is that 30%, which makes our failure 70%. And we have 10 candies that we're actually looking at that we're considering. So this is simply 10 choose 6 times 0.3 to the 6 times 0.7 to the 4. Okay, so there's 10 candies and we're choosing 6 successes. Probability of a success, 0.3 to the exponent 6, which is the number of successes. Probability of failure, 0.7 to the number of failures, 4. Okay, we don't have to calculate them. That's fine. B, what's the probability that 3 or 4 of Vanessa's candies are red? So what we're focusing here is the probability of 3 or 4, and we're going to add those two probabilities. This is the rule of thumb. So we're going to repeat. And just to let you know, 10 choose is not going to change. 0.3 is not going to change, and 0.7 is not going to change. All that's going to change here is that now we want 3 successes. So 3 successes, meaning 7 failures. That's it. And again, 10 choose is not going to change. The probability of a success and the probability of a failure is not going to change. But this time we want 4 successes. So 4, 4, 6. Okay. Now C. What's the probability that at least 2 of Vanessa's candies are red? Okay, at least 2. So we have 2 options here. We can either do probability of 2 plus probability of 3 plus the probability of 4 all the way to the probability of 10. Okay, or we can do indirect method. So I don't want to write out the binomial distribution this many times. So instead, I'm going to say the probability that at most 2, or at least 2. I did the wrong crocodile. At least 2 is going to be 1 minus the probability of 0 minus the probability of 1. And that will give us the probability of 2 to 10. So 1 minus the same setup. 10 choose, but this time it's 0. 0.3 to the 0. 0.7 to the 10. Minus 10 choose, this time we're doing 1. 0.3 to the 1, 0.7 to the 9. And that's it. So there's our indirect method. Now D, what is the expected number of red candies in Vanessa's bag? So we can put the expected number of red candies is going to be n times p, which is there are 10 candies and the probability of it being red is 30%. So 3 candies are expected to be red. All right, example 3, expectation and binomial distribution. Okay, so we're going to actually write out a full binomial probability distribution. In an archery competition, Paul has a 35% chance of hitting bullseye on any given attempt. So, determine the probability distribution for the number of bullseyes Paul hits in 4 attempts. So, here are the options. All of the different outcomes, he could hit 0, he could hit 1, he could hit 2, he could hit 3, or he could hit 4. Okay, so just to put up here, success is 35, a failure would then be 65%, 0.65. And his attempts, the number of trials is 4. So, a couple things are not going to change here for this entire chart. So, 4 choose is not going to change. Okay? But the number of successes is going to change. We have 0, 1, 2, 3, 4. Now, the probability of a success will not change. Okay, so this is going all the way down. Successes are always 0.35. But the number of successes does change, right? We have 0, 1, 2, 3, 4. Okay, now the probability of a failure, 0.65, also doesn't change. Just the number of failures is going to change. So as a recap, these numbers have to add to n. So if we had 0, now we have 4. 1 and 3, 2 and 2, 3 and 1, 4 and 0. This might be one of the only times that we have to actually calculate. So 0.65 to the exponent 4. I get 0.1785. I'm going to go 4 decimals. Zero 0.3845. And I get 0.3105. And this one I get 0.1115. And this one I get 0.0150. Okay, if I were to sit here and actually add up 0.1785 plus 0.3845 plus 3105, 0.1115 plus 0.0150, okay, this does add up, here we go, to 1. Okay, so even with the rounding errors, it's actually perfect. Okay, so now, in regards to expected value, what we're going to do is we're going to multiply xpx, okay? Because we made the probability distribution. This chart up until now is how all of the probabilities are distributed. Now we're going to go ahead and calculate the expected value. So 0 times anything is 0. 1 times anything is itself, 0.3845. Okay, 2 times 0.3105 is going to give us 0.6210. Now 3 times 0.1115 is going to be 0.3345. And now, so now 4 times 0.0150 is 0.0600 if you want to round it to 2 decimals or 4 decimals. Okay, so now when we add them all together, we're getting 1.4. Okay, so that means, interpretation-wise, that means, is it Paul? Paul is expected to hit the bullseye 1.4 times. Okay, now we're going to go ahead and graph the probability distribution as a histogram. Bar graph. This is discrete. Okay, and it's discrete data because our random variable cannot be a non-integer. Okay, so 0 times, and we're going to just branch over. 0 times is 0%. I'm going to just put like a horizontal bar there. Oh, no, I was looking at expected value. 1785. So 1785 will be about here. Okay, probability of hitting it once, 3845. Probability of hitting it twice, 31. 3 times 1115. And then 4 times 0.01. So really little. Okay, so then this will be the probability distribution bar graph.